Okay, so good afternoon, everyone. So this next one will be again a perspective talk. The next two talks are listed perspective talks. The first one will be given by Mr. Tanushree Sharad Gupta. He does not need any introduction here, but not only here, even in India, she does not require any introduction. But still, for the sake of formality, I have to tell, she did her PhD from Edinburgh Center itself. And then she did two postdocs, one from Onira Paris, and the other one is from Max Planck Stuttgart. And she has a number of awards in her credentials. For example, some of them I'm mentioning. She is the fellowship holder of all three Academy of Science in India, and alongside of J.C. Bose Fellowship, Arno Jayanti Fellowship. There are many more. The list is very long. But without wasting much time, I would like to invite her to deliver the lecture. Today she is going to speak something very interesting. Probably the shortest title I have ever seen, from materials to models. So I'm looking forward to your talk.
Good afternoon, everyone. Uh, since this is the talk after lunch, we keep people awake after this kind of heavy lunch is difficult. I know that very well, so I will try to make this talk as less technical as possible. And please feel free to interrupt me whenever you feel you need to ask a question. You don't need to wait till the end. So I repeat once again, I actually congratulate the organizers, especially Ranjan and Indra, for this really great effort, and I do hope it continues. So as Shashata said, that yeah, it's a short title, but you can say a lot in this short title. It's from materials to models. I mean, so far, what you have heard are the techniques to handle real materials, apart from the previous talk, which actually brought in some flavor of models. But somehow, you need to final goal. If you really look at the title of this school, it says experimental realization. For experimental realization, actually, you need both. You need materials, you need models. So somewhere you have to connect this. And as you all have heard, and that is all we have been doing for the last 2 days, is looking at the properties of the electrons, because for most of the properties, actually the key role is played by the electrons. Reason is simple, because electrons are behind the chemical bond. It's the glue that binds them together. And one of the motto for basically computing materials is to calculate the electronic properties in an ab initio or first principles way. And we have heard of two different kinds of first principles method. One was the density functional theory based local density approximation calculation, and the other was Green's function based, more sophisticated GW approach. But both had the flavor of calculating the electronic properties in an ab initio. Okay, so here basically a statement why such kind of calculation is necessary. The first argument is very simple. It gives a way of calculating the properties of material before it can be tested in time-consuming and costly laboratory experiments. And if we think of material discovery, as was touched upon in the talk by Prashant Sen, we definitely need to compute things before we attempt to give it to the experiment. And the advantage of first principles approach is that it retains all chemical and structural information, and most importantly, it provides a microscopic understanding, because many times the experimentalists will measure something, but they don't have the complete understanding. So there is this triangle, which I think is essential. The message of any first principles, electronic structure calculation, you have this vertices, you have been given a composition, and often structure. Even these days, the structure can be even calculated. And finally, the goal is to calculate the properties which are based on electronic behavior. And this is the kind of flow chart which by this time you are all aware of, which basically iterates between solving two equations. One equation looks almost like Schrodinger equation, but it is not a Schrodinger equation because the potential actually depends on the electronic density. So that makes the problem a non-linear problem. So that is why you need so much of trick and things to really handle this. And the other is the Poisson equation, which is basically an inversion problem given the electronic density. How do you calculate this potential? And you basically iterate between the two. And it has many advantages. You can calculate structural stability because the energies can be calculated pretty accurately. You can calculate band structure, although that was not the original goal of the density functional theory because it was primarily a ground state theory, but it looks like it can actually describe, in most of the cases, the bands accurately, and that gives you an access to optical properties. Of course, yesterday, the GW method has been described, which is a much more accurate and correct way of looking at the optical properties, because as mentioned and stressed, you should be clear in your head that the density functional theory, being a density-based theory, actually doesn't have concept of electrons like it was in particles. That concept it doesn't have. So the band structure, where the eigenvalues, you can't actually interpret them as the energy of some quasi-particle. So should have, we are interpreting the DFT calculated band structure, but if you are a pure person, really you shouldn't do it. You can calculate the phonons both in harmonic and quasi-harmonic approximation, therefore giving you the access to Helmholtz and Gibbs free energy. So far all were 0 Kelvin calculation, but you can also do finite temperature calculation through ab initio molecular dynamics, which basically unifies quantum mechanics with classical molecular dynamics by treating the electronic degrees of freedom by solving the Schrodinger or the Kohn-Sham equation, which is fully quantum mechanical in description, while the ionic degrees of freedom, which are much heavier compared to electrons, are treated classically by solving the Newton equation, and these two being connected by the Kelvin-Feynman force, because the force acting on the ions are calculated in a fully quantum mechanical way by solving the electron problem. However, this is not enough for strongly correlated electrons, and that's where all this business of modeling comes. Because even the GW method, as was discussed yesterday, it will work. It is a summation of different diagrams. So unless you really take into account certain diagrams, it will not work with the strongly correlated electrons. Okay, so strongly correlated electrons, the conventional band structure within the framework of the local density approximation is surprisingly successful. Actually, it is doing far better than what it was expected to be done, because the exchange correlation is basically obtained by solving the problem of that of a J-Liam model, which is a quickly correlate with non-interacting thing. But the fact they work for most material is a surprise, but it says actually that such kind of treatment is already enough. However, there are exceptions. That's why this talk is being given, that they fail for materials with strong electron-electron correlation. Correlation effect necessarily arises, and they provide a natural way to understand some of the phenomena that I'm just going to flash. So what are the predictions from local density approximation, which is a simple band structure? So what you have here is the band structure, which is the energy dispersion, energy versus K. You all have seen that. Now, this is a non-spin polarized calculation. So each of the band can hold an up and down electron. So if you have even number of electron in the R in itself, then necessarily the density of state at the Fermi level is 0. That means it's an insulator according to the band structure calculation. But now suppose you have an even number of electrons in the unit cell, but there is an overlap. For example, at the Fermi level, there is an overlap between this conduction band and valence band. Such thing can also happen, and that gives rise to a tiny electron pocket and hole pocket which will compensate each other. So if you have even number of electrons, not necessarily you will get an insulator. If you have a band overlap, that will give rise to a metal. Can give rise. But suppose I have an odd number of electrons, then I have no escape. I will actually have a partially filled band and no other risk. So if I have odd number of electrons without doing any calculation of all of that, you can say that will give rise to a metal by one electron kind of theory. But in reality, is it always true? Let's consider a lattice consisting of some sodium atom. We all know sodium is a metal. So the valence configuration of sodium, just to check whether you are sleeping.
1s2, 2s2, 3s6, 3s.
3s. Very good. So we are not showing 1s, that's deep. So we have 2s, which is we have 2s, which is fully filled. We have 2p, which is fully filled, and we have 3s, which is half filled. And this is half filled band. So according to band structure, it will be a metal. But now I take this lattice of sodium atom, and artificially I apply a negative pressure. By applying negative pressure, you are basically moving these atoms from one sodium atom to another sodium atom. So what is the consequence of it? Your bandwidth becomes narrower and narrower. If you remember the tight binding, simple tight binding model, it's related to hopping. Your hopping becomes smaller and smaller, and therefore your bandwidth becomes narrower and narrower. And if we really put them significantly far apart, it will be like just some energy levels. But even if it has become an energy level, it is still half filled. And band structure didn't tell me what will be the bandwidth and all that. So it will be still a metal. And which is, of course, the wrong result. Because then it will be a collection. Yes.
This will mean stretching.
Stretching. Yeah. So by some means, think of that you are pulling the atoms further. But that is actually absurd because this cannot be a conductor. So something has gone wrong somewhere. What has gone wrong? To have a conduction, the electron has to move from one side to another side. So we start with some neutral sodium atom and the electron moves from one side to another. That's the hopping process. By doing that, what I create is a sodium plus and a sodium minus. Suppose the energy of the sodium 3s was epsilon 3s, then that energy of sodium plus is 0, while for the sodium minus, which has 2 electrons in the 3s, is 2 times epsilon 3s. Right? That would have been in the band structure picture. Adding
There are the
there are
energy levels.
yes.
Electrons are moving. Right. So
No, in a lattice you will have a band. You don't have energy level. Rather,
Yeah,
you have
but-
energy bands.
bands are
No, it's important. Whether you got
for a given day, we have the level.
yes, correct.
So these levels are for the whole lattice. Right. So they like electron is one side to the
Yes.
side.
So that is why I'm saying you must all have known what is a tight binding model. So if you know a tight binding model, you can go back and forth between real space and K space. And in the tight binding model, you have a hopping interaction, and that hopping interaction, if you go to the K space, you will have some cosine K or something that gives you the energy dispersion. The energy dispersion, what you said, the band structure that will have different energy level at one K point, but in the other K point, these energy levels are different. That gives you a dispersion. And that dispersion comes from the hopping. If there was no hopping, there would not have been any dispersion. So then we are adding a certain term, and that's called the Hubbard U term, which was introduced in the previous talk. So where there is an energy cost the moment you are putting two electrons at the same side. And in the band structure, this effect is really not taken into account. If we take these into account, then of course there is an energy cost the moment the electron is moving from one side to another side. Now you can say this U was present also at this lattice constant. Why it didn't matter? So it's a competition. I gain some energy, kinetic energy, by moving the electron from one side to another side, but I also lose an energy by creating double occupancy by putting two electrons at the same side. Now the energy by putting two electrons at the same side is U. That's an atomic property that also depends on screening in case of a real compound or anything, but that's certain specific property. But what can change is this hopping. So when my lattice constant was small, my hopping was large, and therefore the kinetic energy gained overcome the energy loss by creating double occupancy. In this case, the kinetic energy gain is really small because I have put the atoms apart from each other. So you can see already the effect of this rate term U depending on in which regime you are in. I started with certain concrete case. Take the case of the cobalt oxide. You count the number of valence electron, that's 15, an odd number. According to band structure, it should have been a metal, but it is possibly one of the toughest insulators that is known. So there is certainly failure of the simple first principles band structure within the framework of the density function. So what are the examples? One example can be transition metal with a d electron. Why the d electron? The correlation will be important because, as you all know, in a transition metal, you have the unfilled d shell, which gets covered by the outer s shell. So therefore, the d electron of one side and another side, they cannot see each other very well because they are covered by this. As a result of that, they tend to be localized. So throughout the 3D series, even more for the 4D transition metal series, the d electrons are localized but also have an itinerant character and giving rise to the quasi-particle band that was actually shown by Manish. That is what is meant by quasi-particle bands. And electron correlations have important physical effects, but not the extreme one like localization. F electrons. There are F electrons. They tend to be localized and itinerant. The correlation effect becomes much stronger. That of the d electrons, they contribute little to the cohesive energy because they are very localized. But many of these F electron systems are metal because of the presence of other electronic bands, not necessarily the F band. The actinide, which is 5F, they display a behavior intermediate between transition metal and rare earth. And electron correlation actually becomes apparent, more apparent, when you mix some rare earth with something like aluminum, some compound. Then it becomes even more important. And this is reflected, the correlation behavior, in terms of extremely large effective mass, which actually leads to some heavy photon behavior, which shows a phenomena like Kondo effect, where you have a local magnetic moment that arises out of this F electron, and then you have other electrons that gives rise to a conduction bar, and below certain temperature, this local moment can get screened by this conduction bar. That's your Kondo temperature. Above the Kondo temperature, this local moment shows up because the screening becomes weak. So the other example, which actually is probably all my examples will be drawn from this family, this is that of the transition metal oxide. So I just said the transition metal, they are metals. So they still have not gone to the extreme situation of complete localization and being giving rise to an insulator. But if I make these transition metals sitting far from each other, as in the transition metal oxide, here each of the transition metal is surrounded by some of this oxygen because they are not only transition metal but also oxygen. So therefore, one d electron cannot even directly see another d electron. It has to pass via this oxygen. So that makes the correlation effect of a transition metal when you make an oxide even more. Okay, so the strongly correlated electron materials, one needs to have a better treatment for electron-electron correlation than a simple local density approximation. And that calls the need for different many-body techniques, and I think that will be taken up more in the second part of the school. So we have this two class of approach, and that is exactly the talk is in between these two approaches. You have first principles kind of approach, which is material specific. They fail for, that's the plus point, but they fail for strong correlation, being material specific that has the ability of connecting the experiment. And the model approaches, the input parameters of the model are vastly unknown, but they account for the correlation. So the idea is improve the description starting from such a kind of material specific first principles calculation and then get into this model kind of approach. So this model should be derived out of some first principles calculations. So need modeling, keeping the essential rigor. The model are simple things to understand a complex behavior, but we should not compromise with the essential that is needed to be detailed. So ab initio electronic structure calculation, as we all know, that's your condensed system where you have some periodic potential, and basically it's the situation where the kinetic energy of the electrons are in balance with the potential that is created by your nucleus or ions. And there are different methods to solve this problem. The Gaussian, loved by the chemist. The plane waves, loved by the physicist. The physicists love it because then you can really take the advantage of a Weyl transformation. And I think most of the talks, although the basis was not explicitly mentioned, but they actually used the plane wave basis. They had that in mind. In my talk, the kind of basis that we used is what is known as Marpin-Tin orbital, and they kind of is intermediate between the two because the potential where your ions are sitting, they are D, attractive and spherical symmetric. So you can use actually partial waves. Remember your hydrogen atom solution. And in between these two deep wells, there is this part which I call interstitial, where you can use some plane wave and you make a connection between this partial wave and the plane wave. The plane wave you can express in terms of Neumann and Bessel function, and this is just a boundary condition matching problem, and you can get right to some basis set which are known as Marpin-Tin orbital. So what is the goal? The goal is to find a generally applicable electronic structure method which is fast and accurate. I give a stress on intelligible. Most of us use it as a tool for just calculating. Please don't do that. This actually offers much more than. So your method needs to be intelligible. Yes.
Just one question. So if you want this orbital is then
Yeah, I will come to that.
okay.
I'll come to that.
That planar cannot take care of.
I'll come to that.
Yeah.
I'll try to, tell certain advantage. So this is again this band structure which you have seen so many times in so many slides. It's very complex. If you have a complex material, if it is not silicon, so many bands are going up and down and we don't know what they are doing. So it's complex, rarely interpreted. Very few people try to interpret the band structure. needs filtering to be useful. We need to add some filtering to make it useful, and that is what we will be doing. Downfolding and one-yearization. The one-year functions have been already introduced to you, but that was designed as transformation from the block wave. From block wave, you can create the one-year function. That is why it was shown like that. But in the case of the muffin-tin orbitals, this by construction of your basis set, you actually create the one-year function. It is not you create the block function, and from there you use what is known as maximal localization. You basically minimize the spread of your one-year function and get it out of that. And then there is actually a risk. I think I forgot who was showing that. I think Jejun was showing that there was the manifold of the bands and some tiny things were overlapping, and you have no idea what to do with it. Simply because of the fact that there is actually no chemical inside that is incorporated when you are making such one-year functions. So therefore, there are certain advantages, starting with the basis that itself will serve as a one-year function. So, well, the goal is to add chemical reality to physicist model, because without adding this chemical reality, will be off from the materials. So the first example that I will show is that of the ITC cuprate. I think in this almost everyone has heard of ITC, right? So this is the phase diagram of ITC cuprate. So these are structurally copper oxygen plate. Copper surrounded by 4 oxygen, as is shown here. And then you have this copper oxygen plate and stacking of them. And in between different copper oxygen plate, you have some of the doping layer or insulating layer. They can be lanthanum oxygen, mercury oxygen, barium oxygen, even more complex things. And what it shows, this phase diagram, so you can electron dope as well as hole dope, which is shown here. But unfortunately, the same material, you cannot both electron dope or hole dope. They are different. And without the doping in this copper oxygen plate, this is an antiferromagnetic insulator. And as you are increasing the doping, a superconducting dome appears with a dome-like shape, as you can see. And what causes this superconductivity is actually, people have idea that it has to come from the strong electron-electron correlation, but the precise nature of the driving mechanism even today is actually developed. But what is interesting is that if you take the maximum point of this dome, which is this maximum point of this dome, by the way, is called an optimal doping. At the optimal doping, the transition temperature that you get for the lanthanum compound, La2CuO4, is something like 40 Kelvin. But the same copper oxygen, you take the mercury compound, mercury barium copper oxide, that temperature is 90 Kelvin. So whatever is causing superconductivity, there's a lot of material dependence. Our goal is to basically get the room temperature superconductivity. So for lanthanum, it is 40 Kelvin, but for mercury, it is more than double. It's 90 Kelvin. So why is that? So before doing that, what we thought of doing is take the lanthanum copper oxide, La2CuO4. Actually, this material, all of these, they can appear in 2 structures. One is called the T structure and one is called the T prime structure. For example, if you hold dope, lanthanum is 3+, you are replacing lanthanum by strontium or barium 2+, replacing some 3+ with 2+. So therefore, these are hold dope. Or you can take lanthanum and replace it with some kind of cerium or something, 3+, 4+. That will give rise to a T prime structure. So electron doped are of one structure and hole doped are of one structure, and electron doped is of another structure. Structurally, there is certain difference. In case of the T structure, there is this copper oxygen plate, But there is this oxygen which is out of plane oxygen, and that sits just above the copper atom in case of the D structure. In case of P prime structure, this oxygen decides to change its place, and instead of sitting just above the copper, it shifts and sits above the oxygen in the plane. That's all it has happened, nothing more. So copper here is an octahedral environment surrounded by 6 oxygen. Here it's in a square planar arrangement surrounded by 4 oxygen. And that actually made a big change. So this is an experiment which was reported in 2005. What they did is actually, as a function of ionic radius of this lanthanide series, if this ionic radius is big, as for lanthanum, it will be a T structure, but as this ionic radius becomes smaller, just going beyond lanthanum, they are all in P prime structure. So what actually this experimentalists did, they replaced a part of lanthanum by some of these, and by that, even the pure lanthanum 2Cu4, they could stabilize in P prime structure. So that they considered as a route to synthesize La2CO4 in P prime structure. Well, the surprise came when they measured the resistivity. They found the resistivity in the street structure, first of all, 5 to 4 order of magnitude larger than that of the T prime structure. And looking at the temperature dependence of this 2 resistivity, while the T structure is clearly insulating, the T prime structure is almost metallic. So what causes this big difference? Well, this paper created certain sensation, but then people criticized because all the samples were in film form. So there were issue of strain, oxygen content. So we thought of investigating it with our calculation. So this is the band structure of the T structure lanthanum cuprate and T prime structure lanthanum cuprate. The zero of the energy is set at the formula. Very simple band structure. Only single band is crossing the formula. And this single band, if you are not an expert, it looks pretty similar between the two. You can actually calculate the Fermi surface of this single band that is crossing the Fermi level. These are the Fermi surface. You can see that actually the shape of the Fermi surface is quite different. For the T prime structure, it's more rounded, while for the T structure, it's a bit squarish. Now, what we did is basically the down folding, that is where modeling comes, because what I am interested is only plus minus 1 electron volt. That is what is called as the low energy. I'm interested in the low energy, constructing a low energy Hamiltonian. This is a very different approach compared to the GW, where you connect to as high as possible. This is a completely different approach. We want to be as thin as possible. Okay? So depending on what you want, of course, you will never use such an approach to calculate the optical properties. So you have to be very careful what method I'm using for what. So you find that this single band, and what we did with this downfolding technique is to pick. This is like fishing. You have this jungle of band. From there, you pick this single band that is crossing the Fermi. And that is exactly where it helps. You just asked about this maximally localized Wannier function. You see this yellow band, which is the downfolded band, in comparison with the full band structure. You see at the gamma point, this red band is not going here, rather it's going there. In a maximally localized Wannier function, you will never be able to get it. Here it is possible to get it because you see certain band has certain fatness. The fatness tells you how much of copper character it has. And the copper character at the gamma point doesn't stay here, rather it stays there. So since your basis set is constructed, right, to take into account all this chemical inside, so it actually goes and drops down there, which you will not get if you are doing a maximally localized Wannier function. And that was essential to get this difference between the T and T prime. What is shown here is the one-year function. You have seen a lot of one-year functions. One-year function in the T structure and T prime structure. It's pretty complex. You have the copper x squared minus y squared. So the lobes, positive and negative lobe, are colored as red and blue, and then it makes an antibond to the neighboring oxygen. Tail of this one-year function. The head of this one-year function is like x squared minus y squared, but then the tails are shaped like the oxygen E. And it is not only here, but it's in the farther away oxygen. You can see that it's pretty long range. But it is much more long range in the T prime structure compared to T. And you see the same one-year function. So this is the projection in the copper oxygen plane. You see, view the same one-year function in the out of plane direction. So this will be the copper oxygen plane, and this is the out of plane direction. So what you conclude from this plot, that in T structure, your one-band Hamiltonian, the low-energy Hamiltonian, that is much more three-dimensional. While for the T prime, this is far more delocalized in two dimension, but has hardly any extent in the out of plane direction. So these are the kind of, if you really want to make a chemical trend, try to understand it, such kind of construction is very useful. So you can write it in terms of a simple tie binding Hamiltonian. I think you asked about it. So these are your Hopking integral, and that's where you get on this dispersion. So if you set this Hopking to 0, there will be no dispersion. And as you can see, this T just connects two copper atoms, nearest neighbor position. T prime is along the diagonal, it's a square lattice. T double prime is between the next nearest neighbor. Actually, this Hamiltonian is plenty long range. What we find, there is only one parameter which we call as T prime by T. That's the range parameter that decides the range of this one-year function in this copper oxygen plane. Because the other higher order parameters, Hopking parameters, long range Hopking, they are different powers of R. So that means this tie binding Hamiltonian, you can designate, characterize by only two parameters. One is T, another is this range parameter, namely the R. And we actually calculated it for nearly all known cold doped cuprates, long band, 1001. And through such one-year function construction, we extracted this range parameter, and we found that the range parameter actually correlates with this TC at optimal doping. Higher is this range, better it is for achieving the higher and higher TC. Now back to this T and T prime structure. We find if we calculate the R parameter for T structure, as is already you have seen from the one-year function plot, this is only 0.1, but for the T prime, it's 4 times larger, that's 0.4. But now we have to calculate whether it's a metal or an insulator. And I already mentioned these are strongly correlated electron materials, so we just cannot calculate their density of state and see whether it's a metal or an insulator. So include the many-body effect in this ab initio derived one-band model. And this topic has not been discussed at all, so I have just put 2 slides on it. And in this respect, one major breakthrough is the dynamical mean field theory, which maps the full many-body problem into a quantum impurity problem. We all know what is a many-body. Many-body is a many-body, you take the many-body Hamiltonian, and if you do a mean field, you basically suppress all the fluctuation. That's the mean field theory. In case of the dynamical mean field theory, you suppress the fluctuation and the spatial level, but don't suppress the fluctuation at the temporal level. That gives you the name dynamical mean field theory. So the general idea is the following. Replace a lattice model of itinerant electrons by a single site. That's where you are doing mean field at the spatial degrees of freedom, and which are hybridizing with a self-consistent bath, and that bath has the information of the entire dynamics. If you think of a Hubbard model and single site, so there are 4 different levels. A level which is empty, a level up electron, down electron, and doubly occupied. Right? So the electron can actually make a transition from one to another as a function of time. And that dynamics is completely taken into account in a dynamical mean field theory calculation. So it imposes, it is also a Green's function based method, like what you did heard about in the GW. And what you construct is an impurity Green's function, and in the self-consistency, you coincide that with the Green's functions of the lattice, which is just the on-site Green's function, because all the stress is on one side. And as a result, you get a self-energy which depends on the frequency. If you remember in the GW, I hope that was actually derived, I don't know whether it was derived, the self-energy is K dependent. Here, the self-energy has no K dependent, but has a omega dependent. So it is basically 2 ways of viewing the thing. So note the K dependence of self-energy is neglected. And that's basically the loop you can construct. And these are the, if you just have a simple Bethe kind of lattice and do the dynamical mean field theory calculation, just increase the strength of this Hubbard U, then you can, starting from really like a non-interacting density of state, you can get to a Mott insulator, but passing through something which is known as a correlated metal, because it has signature of this Hubbard band, as well as what is known as a quasi-particle peak. In fact, someone asked during Manisha's talk about the satellite and all that. So very often this is actually called incoherent and this is called the coherent when you are doing any photoemission factor experiment. So different techniques as a function of U over W. If it is small, we are pretty good with doing the LDA. You have very well-defined bands, and you have the density of state. Even in the other limit, very strong correlation. You do repair the LDA by doing some LDA plus U calculation that has not been said in this conference at all, but you can do that. In that way, a gap opens because of the effect of U, and the thing becomes completely localized. You have a lower Hubbard band and an upper Hubbard band. But what is the situation if I have intermediate U band? Then you may have actually signature of Hubbard-like band, but at the same time, you have a finite density of state. In terms of a quasi-particle, in fact, that was also a question about the effective mass. In fact, this quasi-particle, the effective mass is significantly reduced because you actually attain certain lifetime. So they are not like the normal metal. These are strongly correlated metals. And in this T and T prime structure, if you do a dynamical mean field theory, this is a DFT DOS of T and T prime. You have just one band, so the density of state is pretty simple. But you can already find that this density of state for the T structure, this is for T and this is for T prime, it is kind of symmetric around this zero. There's a particle hole symmetry. In case of the T prime, this is highly asymmetric. But this change in this structure, if you do the DMFT calculation, that is shown with this red spectrum, these develops a quasi-particle peak, while this has a kind of a gap. So doing, of course, both the thing at the DFT level was metal, but if you take into account the effect of this strong correlation, that in one case gives rise to this quasi-particle peak and nothing in the other case. So how much time I have? 15. After
25.
So the next example I will like to show is that of the double perovskite. I think in today's talk, I think Jejun actually showed Jejun or so I forgot. Lanthanum 2 NiMnO6. I think you should. Exactly. In fact, we will talk about it. So the general formula we know of a peroxide is AbO3. And if you just make this chemical formula double, then it becomes A2B2O6. Since you have B2 instead of B, you can actually accommodate two different transition metals, namely B and B type, and you can manage, the chemist at least been able to do, where the B and B prime side can be made ordered in a checkerboard fashion. And since now the formula has become doubled instead of peroxide, they are known as double peroxide. And there are a lot of applications of such materials have been made. And we'll focus on one such material. The name was at least shown in previous talk, La2NiMnO6. And this is a ferromagnetic insulator. First of all, ferromagnetic insulators are very rare. Most ferromagnet we know of, they are metals. Insulators are antiferromagnetic. So they are ferromagnetic insulators. Even if you have few examples of ferromagnetic insulator, they are of low magnetic transition temperature, at least below 100 Kelvin. I mean, cadmium, chromium is 90 Kelvin, but still below 100. While this one actually created certain sensation because this temperature is 280 Kelvin. So why is that? First of all, so I will just try to show how it helps to make the modeling, making a connection. In fact, in also talk, I think all these J's were introduced. How to really rationalize. In fact, it was also said we can understand the antiferromagnetic J. Ferromagnetic J is much more complex, how that is generated. So I will show them because it's an example of a ferromagnetic insulator. So we can actually, since it's an insulator, we can use the concepts of the superexchange. So as it so happens, so of course, this is La2MnO6. Lanthanum is 3+, oxygen is 2- anion. So together, manganese and nickel can be both 3+, or one can be 3+ or 4+. Both are possible. So manganese here happens to be in 4+. The calculation shows that. Also measurement shows that. And nickel is in 2+. So in an octahedral environment, there will be splitting of the D level into T2G and EG. In case of manganese 4+, D3, so I have T2G where there are 3 upspin electrons and EG is empty. For nickel 2+, D8, T2G is dead because it's completely filled, and in the EG, it's half-filled. So that is the situation. Now, what are the kinds of super exchange we can think of? One is between nickel EG and manganese T2G. So if we have the spins on both the manganese side parallelly aligned, then it is not possible because according to the Pauli's thing, and was shown also by also that this is not possible. But if they are anti-parallel, it is possible. Although I have an energy cost due to Hubbard, Hubbard is unhappy but still allows it. Manganese EG, nickel EG super exchange. There is another part. So in this case, if they are both parallel, actually it still happens because if I think of this EG, because which is empty, and that actually makes Wundt very happy because in this way I'm maximizing the spin at a particular side. Hubbard is exactly the same thing. It can allow, but it will remain unhappy because I'm putting electrons at the same side. So then what is the net magnetic exchange? Is basically the competition between these and that. Because this one allows a ferromagnetic channel, this one doesn't allow a ferromagnetic channel. So in this material, therefore, you have a ferromagnetic channel, you also have an antiferromagnetic channel. You have a competition between the two. Now, you know the shapes of T2G, which are like DXY, XZ, YZ, while EGs are X square minus Y square 3Z square. In principle, there cannot be any interaction between the T2G and EG. If the angle between this manganese nickel manganese, oxygen, and nickel. Because if you remember the structure, the super exchange path will be like this. So it has to go from one metal side, B side, to B prime side via oxygen. If it was perfectly cubic, this angle would have been 180 degrees. And in this case, your T2G EG interaction will be disallowed. But in this case, as it so happens, because of the distortion, this angle is pretty distorted. This angle, instead of 180 degrees, is 155 degrees. As a result, T2G EG hopping is still allowed, although the magnitude is smaller. It's like 0.02 eV, while the EG-EG interaction between manganese and nickel, which is kind of this kind of thing where the lobes are pointing towards each other, that is an order of magnitude larger, 0.2 eV. But interestingly, it is not only T, but it's also the energy level difference, delta. That is important. And the delta value is much larger between manganese EG, nickel EG, almost 2 eV, while between manganese EG and nickel EG and manganese T2G, it's again an order of magnitude smaller. So the T is an order of magnitude larger, and while the delta is order of magnitude bigger, one goes in the numerator, another goes in the denominator. And if you really plug in all the numbers, you do find these interactions to be ferromagnetic. And we even calculated the mean field TC, which of course was overestimated, and the value obtained was some 340 Kelvin, not too bad compared to the 280 Kelvin that was found. I'll skip this part, and in whatever is the remaining time, I will talk a little bit about the low dimensional quantum spin system. So these are the systems where these are the transition metal oxides with small spin. In fact, whatever was discussed in the previous lecture, most of them had small spin. So what do I mean by small spin? Like copper 2 plus, vanadium 4 plus, titanium 3 plus. This is D1. This is D9. So it has like one hole, and these are one electron. So the associated spin is small, spin half. Or you can take nickel 2 plus, vanadium 3 plus, D2, 2 electron or 2 holes, S is equal to 1. So therefore, your spin is small value. And I think it was shown by also in the previous talk that whenever you have such small spin, the quantum fluctuation, the effect of this from the raising and lowering operator, he wrote this Heisenberg Hamiltonian, had a SZ. In addition to that, he had the spin raising and lowering operator. That gives rise to this fluctuation, and that becomes very critical and crucial when the spin is small. So that is what is quantum spin. Now, what is low dimensional about it? All these compounds structurally are three-dimensional. They are not like nanowire, nanocluster, no. But magnetically, they are low dimensional because magnetic interactions are highly anisotropic. So if I take two copper, they talk to each other magnetically only in certain direction and not in other direction. So if I think of the corresponding magnetic model of it, that will be a low dimensional model. That's where the name low dimensionality appears, and such low dimensionality also helps in increasing this quantum fluctuation. And it can lead to many different exotic things, which I have listed here. And the bottom line is electron-electron correlation is important. So what does the modeling is needed? Often the true nature of the exchange network is not what is expected out from the crystal structure. And I will show an example of that, and with that I will stop. So this calls for the microscopic investigation. These are the effective models. You have already come across the Hubbard-like model that was introduced. And of course, if you're in this model, so this is your kinetic energy term. If you remember the sodium lattice problem, that is the kinetic energy, the hopping term, this energy gain, and this is the energy loss for this Hubbard U. Now, if U becomes much larger than T, then of course you can integrate out the double occupancy, and what you get is a TJ model where J is this term T square over U, as was introduced in the previous lecture. From here, if you really add the half filling, like 1 electron per side, of course the hopping term drops, and what you get is what was shown before, is the Heisenberg term. So the idea is the following: you start with the density functional theory calculation, do the downfolding and one-yearization, get to the effective model, and then you use some many-body technique, which can be exact diagonalization, quantum Monte Carlo, or even DMRG. In next week, you will get introduced to DMRG to get to a physical picture. That's that. And I will just try to kind of show you its importance by taking one example from a work which we did long back. So this compound is actually very fascinating. So here, sorry, just pressing the wrong button. So here the magnetic ion is vanadium, and it's vanadium 4 class, therefore D1. Therefore, this is a spin half system. So what is interesting here, the vanadium here are surrounded by 5 oxygen, and that gives a kind of pyramidal-like structure. And these units then corner shear and edge shear to make some kind of ring. But this ring is extended in this Z direction. So it is not really ring, but a cube. It's a fascinating structure. The sodium atoms, they just sit inside this cube and outside the tube just to give cohesion into the structure. So this is the magnetic susceptibility, and what it showed that it has kind of, you can fit it through a Curie prize, but there are 2 different kinds of slope. There is a change of slope at a particular temperature, as you can see. And interactions are antiferromagnetic, as inferred from the theta. Most importantly, down to the very low temperature they measured, there is a distance of no spin gap. So that was a bit surprising. Why is that? Is the following. There is something which are called ladder systems, spin ladders. So if we put some spins in a chain, that's a spin chain. I talked about this copper oxygen, which is basically a planar spin model. But intermediate to that can be a ladder, where you have basically the spins which are like here. So you have interaction along the delay, also along the ground. And the behavior of such spin ladders, depending on whether you have an even leg or odd leg, is very different. In case of the even leg ladder, actually you can have, if you have an antiferromagnetic interaction, you can make a singlet between the spin here and here. Singlet is up, down, minus, down, up, and 1 over square root of. That's the singlet. So you can make a singlet, and as a result, this even leg ladder will show a spin gap the moment you can generate such singlet. In case of the odd leg ladder, you see you have added 1 more leg in it, and this forms a singlet, but you still have some free spin because of its oddness. As a result, there will be no spin gap in case of the odd leg ladder. But the tube, you can actually think, you can cut it, and you can think in terms of an odd leg ladder, because I actually had 9 vanadiums, I didn't mention it, 9 vanadiums in this ring. So it's an odd leg ladder, but with a periodic boundary condition. I can think it's a closed ring, so it's a ladder if I can close this ladder with a periodic boundary condition. If you do that, then in addition to spin, you have a degrees of freedom, which is chirality, because since I have closed it, I have go either in this direction or in the other direction, and that should actually give rise to spin. But this system doesn't show any evidence of spin. So this, if you do a LDA DFT calculation of this compound, this is basically the so-called band structure, and we are interested only in the bands that are close to the Fermi level, and these are the bands which are basically given arising out of the vanadium dxy orbitals. And through downfolding, what we did, we basically picked up only these bands. And there are actually 9 bands, you can count that. And then what we find, we constructed this one-year function, we find that there are interactions within the ring and between the ring. Within the ring, there are 2 kinds of interaction. One is edge shearing, that means 2 vanadium pyramids, they are connected to each other by 2 connecting oxygen. These are called edge shearing. Other is a corner sharing, they are connected to each other by 1 sharing oxygen. And because of this complex and very distorted geometry, it turned out that both edge shearing and corner sharing interactions are almost of similar strength. The interaction between the rings turned out to be of order of magnitude smaller as kind of expected. So therefore, what you can have actually a model which is very funny is a frustrated model, but it's a partially frustrated model. These are all formed by this edge sharing thing, which is shown with the solid line. But then you have this corner sharing one, which is shown with the dashed line. And most interesting, all corner sharings are not present because 9 and 7 you see are not present. So therefore, it gives rise to a partial frustration. And what is shown here is the exact diagonalization result of this derived spin model to get to the susceptibility with the solid line, with the solid symbol, the circles, are the experimentally measured susceptibility, and the black line is our calculated for the partially frustrated spin ring model. Just to check how good is our model, we consider completely frustrated where we put by hand all this missing dashed interaction. Also, we varied the ratio of this interaction, 2 interaction, the dashed interaction and the solid interaction, and we find actually the DFT gave derived model gave the best result. So I think with this I will stop, and this is basically the message. You have heard a lot about doing the materials in a first principles manner for a strongly correlated thing, which will be actually a focus of the part 2. You will hear about different techniques to really handle it, and primarily for the spin models. So these are very strongly correlated systems, and the modeling is the bridge. So thank you very much for your attention.
Quite an extensive talk on modeling, various types of modeling. I'm sure many of you have questions. Please feel free to raise your hand and go for questions. Yes, over there.
In DMFT part, you were talking about self-energy, and you mentioned it depends on frequency. So in GWF, it depends on frequency, right? So
No, it has no frequency dependence.
in GWF, it does.
There is only K difference. There is no temporal part. The temporal fluctuation is not taken into account in the G. So the self energy that is there has only the K difference, but not really the omega. Maybe we can talk more if you
Yeah,
have any.
I'm confused.
So if you have any, maybe you understood something differently in Manisha's talk.
So any more questions? Yes.
I have 2 questions. First of all, this it said about the Ovenian function. You are constructing somehow from the basis, right?
Mhm.
So I couldn't understand because there we construct the Ovenian function from the block wave function.
Mhm.
So what's the difference?
Yeah, so I didn't go through the entire thing, but the basis here is based on the partial waves. If you remember your lecture on hydrogen atom, so the partial waves has all the angular momentum from where you actually get the shapes of this orbital, right? So your basis itself has this orbital information, which on the other hand, for a plane wave calculation, actually there is no orbital. everything is just e to the power I k something. So you don't have the orbital information. Since you have the orbital information right from the beginning, it is like doing a linear combination of atomic orbital calculation, but in a more sophisticated manner. So to start with, each atom in your calculation has all these orbitals which are considered as a basis, as the basis. Okay.
We are starting from the atomic orbital.
We are starting from the other end, where the basis itself is constructed in a way that will serve as your quantum function. I think the contribution here is you can even do what is known as a downfolding. That means you have so many bands. From there, you don't throw away bands. Rather, you fold them in the tails of the one-year function. If you remember the one-year function picture that I showed, maybe I can go anything show. Like this one. So you have vanadium X1. That is just this much. That's your atomic order. But why do you have these little tails? You get all these little tails because you have not thrown away really the other degrees of freedom. Because this compound, other than vanadium, had oxygen, had sodium, and not only vanadium DXY, but also other vanadium D levels. Their effect in certain way is folded. So the picture that you see here is actually the picture of an effective orbital, a dressed up orbital, which at the central part has the main character, but the tails are shaped to take into account of this dressing.
And one more question I have. Because I have seen Manish also. You have why do you prefer LDA for the comparison? Because
Sorry.
LD.
local density approximation.
No, I didn't get your question.
You say many times like LDA gives this band structure, and whenever we improve it, we add the methods with the LDA, then we get better results, right?
No. The
It is
point
like-
is the exchange correlation in density functional theory. I think Manoj Harwala went to a great extent. So how do you calculate the exchange correlation? That is the crux of the matter. So local density approximation is the simplest approximation you can do.
Yeah.
Of course, you can do some gradient correction. Doesn't matter. Whenever we are saying LDA, we are basically all this kind of calculation we are putting under one level as LDA. But you can use GGA. You can use GGA with a different flavor.
Okay, task
Doesn't matter.
So task is simply, let's say we have some
So,
density
in
function.
case of the local density approximation, you replace the problem by a completely local problem. If you remember Manoj Harwala, we started with Hachifok, which was a completely non-local problem. From there, you went to a local problem, right? In the gradient correction, you are just doing a small correction to that local form, right?
He is possibly asking GW, right?
No. He is saying
my question-
when you are talking about the pitfalls of something, you are just always saying LDA. By LDA, what we mean is a class of these. All of these, the GGA, LDA doesn't matter. And there are different flavors of LDA, different flavors of GGA. But they are all belonging to the same thing.
Okay, so if any of you are having any questions, please feel free to ask. Yes. Can you give
What's the picture? What's the picture?
So somehow you told that at some angle the super exchange interaction is dominating. So can you please little bit elaborate on
Yeah.
that?
I will. I actually went to the class. I think you were mentioning of this.
Yes.
Yeah.
Yes. So it at 155 angle.
Yes. So think about it. Think in a very simple way. Think it like an overlap of two one-year functions. Think it, the hopping you can in a simplest way actually think also as an overlapping. So it's an overlap of two one-year functions. So this lobe is pointing towards this lobe. You can see that this lobe here is colored as red and cyan, right? And on this side, it is colored as magenta and some little orangish color, right? And at these connecting oxygen, the tail, which is like this, they are meeting each other because you have all four colors. Right? That is where they are overlapping. Just geometrically, if it was 180 degrees, they were not bent, they will directly connect to each other. That would have been the strongest thing, right? Now, the more we bend, we are weakening this. If you remember, so this is basically some cosine of this angle that is accurate. If you have, instead of that, a T2G orbital, EGs are the orbitals which point towards oxygen. T2Gs are the orbital where the lobes point in between the oxygen. If this angle was exactly 180 degrees, this hopping, which connects EG and T2G, would have been exactly 0. Okay, so you see that this little bent actually do all the music. Sometimes we think these are irrelevant things, but these are relevant.
Thank you.
Hello, ma'am.
Hello. Yeah, ma'am.
Yes, yes.
Ma'am, you mentioned about the DMFT in which you put a magnetic impurity on the path,
No, no. Yes,
like some d orbital or something like that.
right.
But there are cluster DMFT methods also which you might have worked on. So I just wanted to know in what conditions we use this cluster method.
Yes, I just now mentioned that your self energy has no K dependence, has only the omega dependence. Suppose you want to introduce some K dependence. So what do? You have to consider some of the spatial fluctuation. If you are converting the whole problem to a single side, you have no way you can include any spatial fluctuation. But cluster is the way, in that way, at least some part of the spatial fluctuation we can take into account. So that was a way to take into account some of the K factors. So of course it depends on what kind of system and all that. I mean, I don't have any slide. In fact, there are attempts to even combine GW with the DMFT calculation in order to just get the good features of both of them.
Thank you.
Okay, so maybe some online people
I
have some
think there
questions.
were someone was saying something.
Yeah, yeah. That's it.
Somebody raised. Yeah, Divarko Datto.
Devagara Datta, please go ahead.
Hello,
to
ma'am.
Ask the question.
Ma'am,
Yeah.
I have a question. Ma'am, in the slide where you are showing the La2Ni, the double perovskite magnetism. So, ma'am, in that case, you showed the values of the hopping parameters. Ma'am, how these values can be calculated?
So the values were calculated first of all, as we said, we can construct the one-year function, right? So taking this one-year function as your basis, you can actually construct the real space Hamiltonian. And these are diagonal components of this real space Hamiltonian gives you all the t's, while the diagonal components and the differences gives you the information of delta. So once you construct the one-year function, you can actually calculate the tight binding Hamiltonian in the basis of one-year function of manganese T2G and manganese T2G EG, or 5 levels of manganese, and for nickel only 2 levels. So in case it will be actually a 7x7 Hamiltonian, and you can write the corresponding tight binding.
So, ma'am,
I-
without introducing one-yearization, we can't be able to calculate these hopping parameters, right?
Yeah, the hopping parameter is a real space description. So you need to go to a real space description And these 1-year functions are basically helping you to get into a real space description. So all the electronic structure code, these are all periodic code and they all work in K-space. But to visualize everything, you need to go to real space. So we are going to the real space. Does that answer your question?
Yeah, ma'am. Okay, thank you, ma'am.
Okay, so if there is any more question, please raise your hand. Otherwise, let us thank the speaker once again for this. Okay, so let's meet outside for the tea and then we will start the next part.